So we are up to here. If you just summarize, at the beginning, for some small interval, I took you to the journey, the virtual journey in our research activities. Then I introduced the metamaterial inspired techniques, very brief of metamaterial, different kind of structures, MNG, DNG, ENG, and the combination. And then I showed some application in terms of different filtering structures and etc. And last leg of the presentation was on different kind of 5G antennas. I showed two different kind of applications. One is the base station, another is the your user equipment applications, where I talked about some designs which are for sub 6 GHz application, and then that too we showed some SIR loading technique, and then for millimeter wave 5G also for user equipment perspective. So different designs, sub 6 GHz and millimeter wave integrated together also I showed. So now we'll be going to the last leg of the presentation, where I'll be talking about the antennas for cognitive radio applications. So let me go to the full screen mode once more. And as you can see over here in this particular part of the presentation, which is antennas for cognitive radio. So we really need to understand what is the meaning of cognition or the cognitive radio. So as we will be seeing in next 40 minutes or 45 minutes or whatever or so, so here the antenna requirement is quite different compared to the conventional antenna requirement. So basically we have to think of multifunctional antennas, and a single antenna needs to cover multiple operations, that is called sensing as well as communicating. So I initially developed the concepts of cognitive radio, definition of cognitive radio, antenna requirement, and I'll be talking on few designs which have been proposed by other research group, mainly the design by Professor Christodoulou, because he has designed some of the structures, some of the mechanical actuation and the electronic actuation for designing multifunctional antennas using multiple radiating elements. And then I'll be coming to work that will have contributed towards that direction. As already mentioned earlier, for this part of the presentation, you should refer to our articles, IEEE articles, and the book. So this book is very recently published, and I hope in some of the universities and some of the top universities they will have a copy because for individuals it's a bit difficult to buy because as you know these are international publishers and the cost is a bit on the higher side. But in NIT's and IIT's library, the copies should be available. Before I go into this journey of cognitive radio, I just want to talk about the basic requirement. So since the communication has gone more and more data centric over last few decades especially, for antenna engineers the challenge has been to design the compatible antennas to incorporate the proper bandwidth that is required for different kind of applications. So with this journey and with this motivation, the evolution has been from narrowband to wideband to ultra-wideband, and now people are talking about ultra-wideband, MIMO, etc. If you go back to the basics, the percentage bandwidth of an antenna is defined as like this: FU minus FL by FC is the central frequency of, at which your antenna radiates, and FU and FL are the upper and lower frequencies. If you take an arithmetic mean, then FC is average of FU and FL, so it is like this. So you get 2 FU minus FL by FU plus FL into 100. So from this equation, what you see is the maximum achievable bandwidth is probably 200 because FL0 corresponds to 200. And unfortunately, as you know, FL0 is not possible because FL equals to 0 indicates it's a DC frequency. DC frequency or the DC signal can't be radiated. So you can say theoretically that antenna impedance bandwidth, or in general the bandwidth can be close to 200. You can say maybe 199 is possible, but 200 is not possible. So with these different kind of attempts have been made. These are some of the ultra wideband antennas. This is I showed earlier. This is some hybrid antennas combining the monopole, classical rod monopole, and the dielectric terminals combined together. That part is okay. That is designing antennas with wider bandwidth, but the focus completely shift in a very simple MTech thesis by one gentleman. His name is Mitola. So Mitola's proposal, initial proposal was something like this. You have the power which is radiating at different frequencies, this frequency, but we have never thought about the time. So when you see the time, we see different frequency components, even though these are allocated to various primary users, are not being used. So those are called spectrum holes and white spaces. So this is a spectrum hole, this is a spectrum hole, and so on and so forth. So Mitola's hypothesis was to use this spectrum hole efficiently. That means it is something like your Airbnb model. If you have multiple rooms in your house, and if you are not having the full requirement, you can rent some of the houses depending on the traffic in your city. So that would be win-win for you as well as for the visitors, right? So similar kind of concepts. You have the spectrum holes. Those spectrum holes should be allocated to the secondary users. Then you get a better spectrum utilization and effective enhancement of your communication system and communication network. So these requires an intelligent set of antennas, which are people call it cognitive radio antennas and multifunctional antennas. So it requires a sensing antenna because you need to know where these spectrum holes are available. And once you know that, you have to ensure that you can communicate at that frequency. So you need a reconfigurable antenna. What you see over here is a static diagram, but you try to imagine that this is dynamic. That means different points over here, these spectrum holes are moving in arbitrary fashion. So if you really think in that way, like you have a very wide band spectrum, you have from occupied users, preoccupied users, primary user 1, primary user 2, primary users 3, and so on and so forth. Now situation is because you are saying you know that spectrums are not being used perpetually by the primary users. So when you know that, what you have to do is those primary user spectrum holes are to be allocated to the secondary users. So that calls for a cognitive engine and or a cognitive radio which will be intelligent. So as you can see through this animation, what I am to share and give the message is these spectrum holes can be used intelligently and opportunistic way to have a better utilization efficiency, spectrum utilization efficiency, and these can give rise to some of the advantages like, of course, high data rate, opportunistic spectrum utilization, IoTs and all different kind of new applications are coming, and this goes in parallel with the government of India's recent initiatives on smart city, digital India, etc. So this is the broad perspective of having the antennas for cognitive radio applications. So with this introduction on the last leg of our work, I will be taking you to a journey which is quite a long journey. Earlier I talked about some metamaterial structures, but I will show you some real-time applications as far as the cognitive radio antennas are concerned. So we have ultra-widebands, which is FCC license spectrum in 2002, 3.1 to 10.6 gigahertz is called the ultra-wideband antennas. Of course, there is huge bandwidth, ultra-wideband frequency range due to low energy density. UWD signal is like noise-like, so you have to work below the noise floor because within this band you have some preoccupied users like narrowband signals, and it is evolved from the spectrum wide, like different kind of mechanism like OFDM, then CDMA, and etc. So spectrum techniques has evolved and it has given rise to this ultra-wideband communication. So antenna side, if you really want to have that much of bandwidth, you need to think of some antennas. Like these are some popular antennas which have been reported by various research groups: the spiral antenna, the printed monopole antenna, the notched or tapered slot antenna, and these are the typical Utw antenna characteristics one aims for when you try to design such an antenna. Transit and receive very narrow pulses, directive or omnidirectional. Because when you say my system is wideband, you tell it in terms of the frequency, but time and frequency are orthogonal. Like If your signal is wideband in frequency domain, it's basically narrowband in time domain. So that's why it's the narrow pulses which actually are used for exciting these kind of antennas. So these are some of the designs for ultra wideband applications. So here onwards, the rest of the presentation will be predominantly based on our work. So I'll be talking on initially some frequency notching technique in ultra wideband antennas, even though it is not directly related with the theme of today's cognitive radio and 5G antennas, but you will get a very beautiful correlation from the stuff I will be talking, because these I will be extending for some of the smart and some of the intelligent antennas for cognitive radio applications. So as you can see, this is a bandwidth from 3.1 gigahertz to 10.6 gigahertz. We called it ultra wideband spectra. Within these ultra wideband spectra, as I said, there are some narrowband services sitting. So these are the two examples. One is the WiMAX, which is sitting for 400 megahertz from 3.3 to 3.7 gigahertz, as you can see over here. Right? This is 400 meg, and this is another 700 megahertz for WLAN, centered around 5.5 gigahertz. Right? There are many more narrowbands in between. So we really need to now design an antenna which will be covering full 3.1 to 10.6. If you do that, actually you will be disturbing these preoccupied narrowband services. Also, you will be disturbed by those services because those radiations will be spurious to you, because your band will be affected. So such an antenna which will be radiating over the entire frequency range, accepting these preoccupied primary users, is called a frequency notched antenna. So I like to show some of the work for the frequency notched ultra wideband antenna. Then I will be extending to multifunctional antenna and other applications. I probably shows these two equations previously in another context, but this particular table, if you see over here, the different IEEE standards like W802.11 to 802.11b, and then G, and then 0.151, 0.153, 153A, and then ZigBee, which is indicating this is the feature, and this is most interesting, which is the ultra wideband. As you can see, out of this comparative table, the UWB covers the maximum depth rate, which is more than 100 Mbps, and of course it is for low range applications, so it's within 10 meter and so on and so forth. So with the given situation, if you go for ultra wideband, then you get a good data rate and other features, of course. And as I mentioned earlier, if you have more directive antenna with higher gain and more number of antennas together, like in the transmitting and the multiple transmitter and the receiver side, using the MIMO technique, then you have the advantage of getting even better channel capacity. So that's why a combination of UWB and MIMO is being considered. This slide I have prepared from the content of our book, one of the chapters called the fifth chapter. So here the idea is, before I take you to this journey, let us try to understand what is the meaning of cognitive system. Cognitive system, I hope many of you are aware with the term cognition. Cognition means some kind of inherent intelligence, embedded intelligence that's all the human beings and other creatures also having. So if you are given in a difficult situation, we respond corresponding to the difficult situation, and then we learn. And from that learning, we actuate certain mechanisms which will help us in, to behave properly when we are against such a system. So these such type of capability or inherent features are called cognition, systems. So as per the Oxford Dictionary, the mental action or the process of acquiring knowledge and understanding through thought, experience, and sense is cognition. A perception, a sensation, idea, or intuition resulting from the process of cognition. This intuition is based on the previous experience. And then, as I mentioned, late 90s, this gentleman, Mitola, it was his MTech thesis. I repeat, it is an MTech thesis. So he proposed that if such a mechanism is used where the primary user's unoccupied spectrum can be dedicated to the secondary users, that will lead to a very high spectral efficiency and thereby channel capacity and thereby data rate as well. So this cognition cycle actually is a cyclic process. We call it ODAL, O-D-A-L, observe, decide, act, learn, and accordingly you configure your system. So this was the idea of METLA, and this was supported by two surveys. One, immediately after this proposal that the primary user spectrum can be allocated to the secondary users for a better spectrum utilization. Two surveys were done. One, IEEE formed a body for a surveying, and Professor Rappaport, perhaps you have heard of his name, the famous wireless engineer, he also made a survey by his research group, and both the surveys, outcome or the decision is almost identical for a huge amount of time, like for more than 50% of time, more than 90% of the spectrum are idle. So primary users are not always using their spectra properly. So this was the concept which was used for this cognitive radio, that spectrum has to be used in an efficient manner. Because if I ask on this platform, on this, like, what is the most precious thing, most of the people will say it is gold or platinum or maybe some other kind of noble metal. But EM engineers knows that most scarce and most costly thing is the spectrum, right? So cognitive radio is an intelligent wireless communication system. This is as per the definition by Professor Hekin, right? He is aware of surrounding environment and uses the methodology of understanding by building to learn from this. So you can definitely read out highly reliable communication whenever and wherever needed, efficient utilization of the radio spectrum. This is from Hekin, quote unquote. I have not even used a single word, so you can change the single word. So you can understand that for such a system, if I really want to implement, we need to have a sensing mechanism to see where are those spectrum holes, and then learn, and then we have to act properly. So this requires for a software defined radio. That means it is an intelligent radio which will detect the spectrum holes and accordingly act properly to use those spectrum holes efficiently. So with this background knowledge, we'll now try to understand the evolution of multifunctional antenna. Because now I'm going to propose one set of antenna which will be operational for spectrum sensing, which can be used for communicating, and which can be used for reconfigurable frequency operation. Because when we say communicating, it needs to communicate at different frequencies depending on the different types. So if you come to this classical definition of reconfigurable antenna, you will be getting the frequency reconfiguration, polarization reconfiguration, pattern reconfiguration, and sometimes the combined reconfiguration also. The multifunctional antenna is maybe somewhat close to these reconfigurations, but the idea or the genesis is different. Here the requirement is to design antennas considering the feature, the functional feature. Sometimes I want the antenna to be wideband, sometimes I want the antenna to be notched wideband, and sometimes I want the same antenna to be acting as a narrowband. Not only that, that narrowband operational frequency should be tunable at different frequencies. This is the combined and compact requirements of such an antenna system. So if you dig into the literature on different techniques of antenna reconfiguration, then you will see there is electrical, there is optical, there is physical, and there is material change based reconfiguration. So it uses different kind of, whenever you go for such thing, you have to have some switches in forms of RF names or pin diodes or vector diodes. If you go for optical mechanisms, I'll be showing some of the work by other people. They're using the photoconductive switches, etc. And then we have material change based structure, or you have used different kind of ferrites or LCDs for such operation. And then I'll show some of the work by Professor Christodoulou, where they are using the mechanical structure and the motorized rotation to actuate a different kind of mechanisms. So this is next 5 minutes or so. I'll be talking about the evolution of multifunctional antenna. Basically, you have a tuning arrangement, and that tuning arrangement you apply on a wideband and ultra wideband antenna to extract multifunctional antenna feature. I repeat, multifunctional means we want the antenna system, a single radiator or multiple radiators, whatever is there. We'll come to that part later on. But the system should be operational for sensing as well as communicating. These probably I already discussed, but just to repeat, these are the spectrum holes. Our goal is to detect the spectrum holes and communicate at those spectrum holes for the secondary user. So how to detect? So for detecting, you need to have a ultra-wideband antenna which will be doing the frequency scanning for the entire available range. Whatever the band you are talking about for the entire range, this should be acting as a scanner. So it is called sensing. So it searches for the available space, that is called the white space which is available, that is the spectrum holes. And so once you get that information, you should have secondary antennas which will be used for the secondary users. And in this particular conceptual diagram, as you can see, you have a tunable narrowband section. What is the idea over here? This was proposed by Professor Christodoulou. This part of the substrate, this entire structure is the substrate, but this circular part of the structure is basically separately embedded, and this part is rotatable. How is it rotatable? Because you put a motor on the back side, and that motor actuates this particular rotation. When it starts rotating in this direction, for example, as given in the arrowhead, these one of these n number of radiators which are placed in this way along this circumferential direction, 1, 2, n, and so on. So one of those radiators will be coming in touch with the feed line, and as a result, each of these radiators designed in a way such that their resonance frequencies are different. So one of them will be functional, and as a result, depending on the position of the motor and because of the position of the instantaneous time, one of the resonances are actuated, and thereby these antenna can be operational at multiple frequencies governed by these multiple radiators which are shaped and configured and sized accordingly. So this is the very basic idea of one multifunctional antenna, combination of a sensing antenna and combination of a narrowband antenna in a single platform, but it is using multiple radiators. So this is called multiple radiator based multifunctional antenna. And this is little bit of the theoretical background. As you can see from this Professor Christodoulou's work, I was referring to his name. This is the spectral density or spectral density as a function of frequency. This blue is for the primary users, and you see the white spaces are indicated for the secondary users, and these are to be used for the secondary users in a given situation, and this situation is called spectrum interweave. So in this spectrum interweave situation, you have to identify these holes, and you can allocate these holes to be useful for the secondary users. And there is one more situation where also you have the power spectral density as a function of frequency. This is the frequency axis, as you can see over here. But in this situation, you have the primary users, of course, but in this situation, the requirement is little bit different in the sense here the secondary user can use not only these holes, but also the primary user's frequency. But then if you use the primary user's frequency, then primary users might get disturbed, right? So for that, you have to ensure that secondary users will be operational below the interference level. So this is the interference level. So secondary users should be operating below this interference level, and also using some kind of orthogonal polarization, etc. So the primary users and secondary users can coexist. So this interweave scenario and underlay scenario will be requiring the different kind of antenna requirement. So when you come to the antenna requirement for different kind of situation, this is a functional block diagram. That is, you have a cognitive radio front end. The two situations I talked about, one is interweave scenario and another is underlay scenario. And then you have wideband sensing and narrowband sensing. And under this also you have wideband sensing. And the antenna requirement is wideband narrowband and reconfigurable narrowband. In the second case, it is wideband antenna for sensing, and reconfigure notched wideband antenna. So whatever you do, you need to have an antenna which will be operating for frequency scanning as well as communicating. I mean the for narrowband communicating antenna. So in a nutshell, this is the heart of a cognitive radio, like antenna front wise. Of course, there is communication, signal processing, and some kind of intelligence also involved there. Of course, so this is not only the task of antenna engineers, but also the communication engineers. So in a real CR and SDR kind of platform, actually, it consists of the antenna engineering, wireless communication engineering, and bit of other things also. But in a nutshell, as an antenna engineer or the RF engineer, we now understand the requirement is we have to have a sensing ultra-wideband antenna and a reconfigurable antenna for communication. So these has to be embedded on a common substrate. When I say that on a common substrate, it is up to you whether you will have multiple radiators or you can have a single radiator to cover both the operations. So this is some work which is the contribution by Professor Christodoulou. As you can see, the top left diagram, the scheme I was discussing earlier, and this is a wideband antenna, which is basically ultra wideband. This is a monopole basically, but it is a semi-elliptical kind of structure. It covers the entire 3.1 to 10.6 gig. Result part I am not showing over here because result is obvious. It will be doing the communication. And as you can see over here, multiple radiating elements are placed over here. 1, 2, 3, 4, and etc. So what you are doing is you are moving circular azimuthally. You are moving this particular part of the substrate through a motor. This motor is placed on the back side of this circular region. As you can see in this structure, this part is separately done and it is embedded inside the common substrate. So this is the sensing antenna, and all these antenna elements are separate, and these part gets rotated because of this rotational alignment. Of course, there will be drive to run this motor or actuate this motor. Once you start rotating, different elements will be moving like this, and thereby at a time one of the radiators will be radiating. But there will be proximity effect also. We can, as an engineer, we cannot neglect those. But in general, these will be operational at different frequencies because the size and the shape and the configuration of different radiators are different. So this is the first conceptual report and experimental realization. And some other work are like people are using some kind of reconfigurable filter section in the field region of the antenna. As you can see over here, so there is a different kind of gap coupled structure and etc. Putting some pin diodes or varactor diodes in between the slots, and thereby the antenna response changes. And then there are some other mechanisms also, sometimes more filtering concepts or sometimes the optical concept. In this particular work, as you can see, this is again culmination of quite a few work which is there in our chapter 5 of our book. Like what you see is over here, this is a conventional monopole antenna. As you can see, this is the feed network and this is the circular monopole. This is the conventional microstrip feed. But what is done over here, using some diodes, some additional path is created. So depending on the configuration of the diodes, whether it is on or off, sometimes the straight path, sometimes this path, or sometimes this path can be actuated. So if you incorporate a mechanism like this, then what happens is, like in these diodes, suppose you keep this diode on, D1 on, then you will have only this path and it will be acting as a with a specific antenna response. But if you keep the D1 off, but if you actuate D2 and D4 on, then the signal will be propagating through this path. And this path is a selective resonant kind of structure. So all the frequencies won't be propagating through this. So thereby this antenna, depending on which path is actuated, whether this path is actuated or this path is actuated, it will be giving you different kind of antenna responses. And it requires the pin diode, capacitor, metal via, and some of course the bias pad, because you are embedding the diodes over here. So this is a little bit circuit requirement for coming up with this type of idea. This is a similar kind of structure, but in this case the actuation is done through the optical mechanisms. So you have, as you can see here, you have the switches, but these switches are basically the optical switches. So that is the photodiode or phototransistor. It's a little bit not that straightforward. To actuate this photodiode, you need the lights. These lights are guided through the optical fibers. So these optical fibers actuate some of the switches, and thereby some resonances are excited, some resonances are killed, and in that manner, the overall the antenna, depending on the actuation of different pair of switches, will be acting as a multifunctional antenna. So this was some literature based on the contribution from other group. Now, with a broad perspective, as I said at the very beginning, the frequency notched ultra-wideband antenna, then coming to the dual complementary antenna and multifunctional antenna. So this is the last leg of the presentation where I'll be completely talking based on our own. So first, let us start with the frequency notched UWB antenna design. As you can see over here, this antenna is a popularly known circular monopole antenna. Probably by this time you can see the structure. So here, as you can see, that it's a circular monopole, and the monopole is excited by a CPW feed line. So this is the CPW feed line, ground, this is the signal line, and this is the monopole. And depending on the the radius of the monopole, there will be a fundamental mode which is typically taken at 2.5 gig, and then higher order modes together. It constitutes a beautiful impedance bandwidth to cover the entire 3.1 to 10.6 gigahertz. But that will be covering the entire the frequency range. This tiny set of resonators, which are sub-wavelength resonator, which are called also the magnetic resonators, because the magnetic field of the propagating electromagnetic signal basically excites them. So those resonators are placed over here, and at their resonance frequency, actually this structure acts like a notch filter. So thereby, some frequency components around the resonance frequency of the SRR is inhibited by these resonators, and thereby these antenna radiates over the entire frequency excepting those frequencies. So this frequency, as I have shown at the very first leg of my presentation, is based on the resonance frequency of the square splitting resonator that you can calculate using the closed form expressions that I have described earlier, right? So these are the resonators. The beauty of this mechanism, if you see other kind of antennas, there will be slots, there will be CSRRs, there will be different kind of defects, etc., so on and so forth. But in this particular structure, we don't tamper the antenna, we don't perturb the antenna. The radiators are placed on the ground plane, and thereby this is the side view, and this is the structures, of course. And then, as I said, that you are not disturbing the radiator, and it is independent of the radiator. In the sense, you can have a circular or any kind of structure. In fact, you can have other type of antennas also, like slot antenna, as I mentioned earlier, that different kind of slot profile, like linearly tapered profile, exponentially tapered profile, or tapered slot in terms of balancing and unbalancing structure. So all these things can be extended from here, right? So this particular slide, as you can see now, is basically the the fabricated structure using this CPW fed monopole antenna. And as you can see over here, this is the resonators which are loaded on the back side. Those are not in the same scale because these resonators are sub-wavelength resonator. As you know, the metamaterial kind of structures are always sub-wavelength resonator, falling between lambda by 10 to lambda by 20. So this is the dimension, substrate details, 2.32, like the active dioide 2.33. SRR dimensions, as you have seen, these are very tiny, these are very small. As you can see, by comparing these and these, you are seeing that the connector is much bigger. So these two guys are sitting here, and these are tiny sum wavelength resonators. You can use this calculation, and you can design a beautiful frequency notched antenna. As you can see in this particular plot, the S11 response of the antenna with and without the SRR. So left side is without SRR. As you can see over here, the antenna is nicely matched over the entire frequency range, simulated and measured, right? So there will be bit of mismatch. This is called the fundamental mode, and this is the next mode, and this is the next mode. But if you do the measurement in a very honest fashion, mismatch is very, very expected. That would give the fabrication tolerance and some other kind of inherent experimental difficulties. And when you do this with SRR, as you can see, accepting this frequency notch, which is contributed by the splitting resonators, the performance of the antenna over rest of the frequency spectrum remains almost identical. So this is with respect to the impedance characterization, but as you know, you are talking about ultra-wideband antenna, you have to go for radiation characterization over multiple band. But before doing that, you can actually nicely interpret some of the results using the practical electromagnetic simulator switcher. In this case was HFSS. So as you can see, this particular resonator was designed for typically 6.3 kind of gigahertz, 6.34 gigahertz. So accepting at that frequency, these SRR resonators are transparent. So at this particular frequency, as you can see over here, at 6.34 gigahertz, this antenna is not excited. Why? Because this resonators is a very high Q resonator at that frequency. This causes huge impedance mismatch. So the signal, instead of going in this direction, it's basically reflected back from here. So as I was showing at the very beginning, and I was telling you the metamaterial inspired structure and metamaterial structure. So this is a metamaterial inspired structure, but we have not used the term metamaterial here because it is not having a material concept, because we are not having a big array, a large array, or 3D array. And at other frequency, like this one is at 4 gigahertz and this is at 8 gigahertz. So these resonators are pretty transparent, and as you can see, the antenna is nicely excited at 4 gigahertz and 8 gigahertz because the resonator has no role over here. So at 4 gigahertz, which is at the lower frequency, which is closer to the monopolar resonance, as you can see, the monopolar resonance exists over here with a null here, and you have one maxima over here. Those who are at the very beginning of their research journey, for them these basic concepts are very, very important. You see there is a null here because in a monopole, typical current distribution, as you know, in a classical monopole, if you have a monopole like this, with this as the ground, like this as the ground, and this is the monopole type of antenna, the current distribution at the fundamental mode will be like this in a monopole, with a maxima along here and with a null at the axis. And then if you talk about a higher order mode, then at higher order mode your current will be will have different kind of profile. So the first higher order mode, your current will be something like this, right? And then the next higher order mode, your current will be like this. Always you will have the maxima around the feed point. So that's what I was trying to show here. You see there is a null here, and this is very red here. So this is a null and this is a maxima, which was corresponding to the first case I was talking. This is the monopole, and the current is like this. So at this point you have the maxima, right? Null. Whereas at the higher frequency, as you can see, you have a null here, you have one more null here, another null here, and finally you have a maxima. So this is a much higher order resonance. So null, and this kind of thing. So this understanding is very important for all of you. Okay, so this is the surface current distribution at different frequencies, and to get a more understanding, I just want to show this animation to all of you. So you see the radiation pattern of the antenna at different frequencies. Here the frequency is changing if you follow the bottom curve, and you see the left side is one without SR and the right side one is with SR. So as you can see over here, for the SRR loaded case, at resonance frequency, the radiation is completely ceased. If you have followed it properly, I'll play it one more time. That here it starts at the lower frequency. Now here it typically starts, and then what happens is at resonance frequency, the radiation with SRR loading case is completely shrinked. That is because of the fact that that particular frequency is not even allowed to the antenna thanks to the high Q resonance of the split ring resonator. So this is the 3D measured radiation pattern, because you claim your antenna is a wideband antenna. So you have to observe the pattern at multiple frequencies. So we did the measurement very methodically to various places. And if I tell those stories, it will take a lot of time. How many chambers we have used, like starting from Samir chambers to DRDO chambers to ISRO chambers to chambers at Royal Military College to University of Alberta also. I mean, not on the same antenna, but various kind of antennas. So that's a very useful experience, because these are very small antennas, and measuring the pattern with highest accuracy is very important, because people are using the simulator to show the pattern. But if you really enter inside a chamber, and then you have the standard gain horn, and then you have to do the 2 antenna measurement technique or 3 antenna measurement technique or gain transfer method. Those are very important. So anyway, those who are not having those facilities, you can see those initially at the simulator, but at the same time you should do some kind of friendship or handshaking with some other people who are having this kind of facilities. We are having our chamber going to be installed soon. The process is on. Anyway, so this is the pattern at 3.1 gig, 6 gig and 10 gig. As you see here, you have for all the cases you have the axial null along the axis of the monopole. 3.1, this is 6, and this is 10 gigahertz. These top 3 are the E plane of the antenna, and this is the H plane of the antenna, which is, as you can see, which is almost like a circle, because this antenna is an omnidirectional antenna. And as I was talking just few minutes before, that measuring these radiation pattern of this type of small antennas, I mean small antennas means I am not saying it's electrically small antenna, because it is a conventional monopole only, but with respect to the other antennas, with respect to the structures, with respect to, because inside the anechoic chamber you have other metals also, because you have to have that antenna mast, then you have a horn antenna which is illuminating your antenna under test. So those things should be completely covered. So these are some kind of observers which are covering the cable. So cable is coming from the back side. And even if you do that, the connector is there. This is the 50 ohm connector, which is soldered with this signal line, and the ground goes to the 2 side, because it is a CPW kind of fitting. So these connectors reflection sometimes can disturb your pattern, because you are trying to standardize your pattern. If you get a good pattern with such a combination, then only you can claim that your antenna is proper in the real scenario also. So these connectors reflection also should be mitigated while doing the precise measurement. That's why one ferrite ring is used. This ferrite ring effectively covers this connector fully. Okay, so then you get a better pattern and better that gain plot also, like normalized gain plot. Better in the sense I am saying it is more accurate. So this is the gain transfer method we used, and we use the typical standard gain horn, which is the reference antenna whose gain profile is known, and we have used the antenna under test over here. And as you see, because we are saying it's a notched antenna, see the gain is pretty flat and nice over the entire band, excepting this frequency which is around 6.3 gigahertz, where the antenna gain falls drastically. And this is the reconfiguration of the same structures for multiple notched application. When you want dual notch or more number of notches, you can effectively use more number of resonators. As you can see over here, you have small SRRs for high frequency and large SRR. Sorry, for the lower frequency applications. And this design was reconfigured for 2 different applications. One is multi-frequency, dual frequency notch, and another was for wideband notch. So for that, as you can see probably from here, like you have a couple of resonators here and another couple of resonators here. Here their sizes are relatively varying, rapidly varying. Whereas in this case also 2 pairs are there, pair 1 and pair 2. The size difference between pair 1 and pair 2 is very small here. There is a subtle variation here, and there is a coarse variation here. So these will correspond to two different resonances which are pretty isolated. And a second case, the resonance frequencies will be of course different, but they are very close to each other. So because of the proximity of the two resonances, this structure is effectively act as a wideband notch, and whereas this case will be acting as a dual band notch. So that's why the title of the paper you see, compact dual SRR loaded monopole antenna with dual frequency and wideband notch. So this is for wideband notch and this is for dual frequency. So this is immediate extension of this concept. Like I can talk on these things for hours because this involved so many things and all. But now, finally, I will show how these concepts have been effectively used for coming up multifunctional antenna with a specific focus towards the cognitive radio. So this part is equally impressive and equally interesting. So as you can see on the left side, top left side, it's a uh, schematic diagram, or I can say it's a block diagram or flowchart kind of thing, where you have basically ultra wideband monopole antenna, which is a circular monopole antenna, and this antenna is loaded with SRR with different kind of switches, and sometimes the gaps of the SRR are closed. So together, when you close the gap of the SRR, you call it CRR, closed ring resonator. And then when you have the switches connected between the signal line and the ground plane, effectively the DC or the electrical engineers will call it a short, or the RF engineers will not call it a short because it effectively acts like a couple of inductors here and there and bit of capacitance also. So as you can see here, there is a switch and here there is a switch which are represented by some shunt wire here. So when these SRR and shunt wire are activated together, the same antenna will give a different antenna response now, which is a narrowband antenna response. And the third configuration, it will giving a complete ultra wideband response. First time such an antenna was reported where a single antenna gives three different responses: configuration A, configuration B, and configuration C. So it is just for the users quick understanding. It's a kind of Boolean table, yes no kind of thing. So when you have a SRR and shunt strip, you get a narrowband response. When you have SRR and no shunt strip, that means basically the switches are open, you get a frequency notch ultra wideband antenna. When you have SRR and the shunt strip are again open, you evoke the ultra wideband response. So this is the beauty, and as you can see the structures, the fabricated structures. This is the basic antenna, ultra wideband monopole antenna, CPW fed. You have pair of switches. For the first experiment, both the switches are closed here, and then resonators on the back side. It's a magnified view of the same kind of resonators over here, and you get three different antenna responses invoked from a same antenna. Unlike the Christodoulou's work, where they have used multiple radiators to invoke different kind of antenna responses, here a single antenna gives multiple antenna responses. So we name these antenna as a dual complementary antenna. Dual complementary antenna. Little bit more on this if you extrapolate. Like you have an antenna which is ultra wideband, so you can do the sensing, and then you have a narrowband antenna, and if you can reconfigure this narrowband, if you can tune the narrowband at different frequencies, then these antenna will be a very useful candidate for cognitive radio applications. But only part is, as of now, this reconfiguration is not there. We have ultra wideband sensing and we have a narrowband communication, but narrowband communication is not tunable. So to do that, initially, if you see theoretically, I have SRR. If I can change the dimensions of the SRR, definitely different SRRs will correspond to different resonance frequency, and thereby you can theoretically claim that I have a mechanism by which I can tune these resonance frequencies gradually. But that is just a theoretical claim, because once you print a SRR, you don't have any option to change the dimension. But I'll come to that, how to do that. But you see, the S11 response of the antenna for two different configuration. In one case, it is a notched ultra wideband because it is nicely matched over the entire band, except in this frequency where it is radiating. So it is a frequency notched ultra wideband response. Whereas the second case, the same antenna is now radiating only at a single frequency, which is near the resonance frequency of the SRR. So this conforms to different responses of the antenna, complementary response. The same thing is established from the gain plot. The blue is for the notched case, where the gain is pretty flat and good over the entire band, excepting at the 6.4 gig kind of thing. And the dotted black indicates the configuration B, which indicates the narrowband response of the antenna. It's a good matching for the entire band. Sorry, it's only at the narrowband frequency the gain, the antenna gives good gain, and other frequencies as desired the gain is pretty low. And this particular plot indicates that we have three different configurations measured and simulated together, A, B, and C. I mean, when you have the standalone monopole, it is ultra wideband, but standalone monopole with SRR, but the gaps closed is also an ultra wideband antenna. So you see the similar response for all these cases. And this part, as I mentioned, theoretically, if I change the dimension of the SRR, the large SRR will be corresponding to small resonance, and then there will be gradual resonance shift of the SRR. So if you buy some means, if you can actuate these mechanisms, you have the option to tune this resonance frequency. This one I am talking about, the narrowband, and then you can claim you have a real multifunctional antenna where you have wideband sensing and narrowband communicating, because your narrowband antenna is not tunable. But the question is, as I said, because we have only a single pair of SRR and we can change this dimension, so we have to come up with some other thought process. I'll be coming to that. Just let us wait for a few more moments. And then for this type of antenna, if you want to see the, because you are claiming your antenna is an ultra wideband antenna, then you can see the group delay for two different configurations. Configuration B is measured group delay for the notch case, so you can see the flat group delay over the entire range, and at the notch frequency this is pretty high, right? And the second case you have flat, very flat group delay, which confirms its narrowband nature. And this particular plot I have talked on a few other forums also probably, so you have seen perhaps many of you. So this is an interesting plot which basically plots the pointing vector as a function of frequency and distance. So this is the distance from 0 to around 22 millimeter, which is the feed length of the antenna, and this is the frequency. So these are the two different configurations. As you can see, this colored map, rectangular contour plot, it indicates the strength of the pointing vector along the direction of propagation. So as you can see over here in this top one, the pointing vector is pretty strong for the entire frequency range, excepting a narrow frequency range. So this indicates a filtered energy in the entire energy, excepting a notched, excepting one particular frequency enters to the antenna. So such a filtered pointing vector will correspond to a notched response. Whereas this case, if you see, it just complement of this, because it is red, blue, red. Here you see it is blue, red, red. So here only a narrow band of signal enters to the antenna thanks to the band pass filtering action of the split ring resonator and the copper wire, the shunt wire, the switches I talked about. And then this is the measured response of the antenna for the E plane as well as H plane, considering both copolar and cross-polar radiation. As expected, the E plane is, kind of, I can't say figure of 8 because it is not dipole, it's a monopole, but it is like this with very less radiation on this side. And then the H plane, as expected, is somewhat like a circle. Because it is a narrowband configuration, so we are showing only around the resonance frequency of the antenna. So this is the beauty of this dual complementary antenna. And now I'll be extending this concept a little bit more on other antennas. Probably I discussed this slide earlier in connection with the application, so let me skip this particular one because these are the same type of concept, the SRR loading on other kind of antennas, Vivaldi, balanced antipodal type of structure, and some of our students, especially from National Remote Sensing Center, Hyderabad, they're using the similar concept for designing some horn antennas with frequency notched kind of profile. In fact, as I said, the concept is so unique and generic, you can easily apply it on any kind of planar antennas, ultra-wideband planar antennas for producing a frequency notches. So this is just an example of that. This is, as I probably mentioned earlier, this concept is now applied on antipodal tapered slot antenna with two different configuration. In this configuration, this is placed in the aperture region, where I know that the field will be coupling because your magnetic field will be going like this vertically, so that will excite this antenna. Whereas in this configuration, you have SRR placed very close to the microstrip line, and here also the magnetic field will coupling. And as I mentioned earlier, very strong and sharp notches are obtained with this idea. Now, I'll show how these concepts have been used in designing multiple frequency notched as well as multiple narrowband antenna, because I said that we need to have multiple narrowbands to really claim that it can support the requirement of cognitive radio antennas, right? I'll show that in next 5 minutes, and then I'll come to the last leg of the presentation. So this is based on a rotational circular SRR pair, and that varied pairs are loaded on the different segments of the CPW fed line, and this is the theoretical background for this particular one. So we have a rotational SRR whose resonance frequency is function of the rotation angle theta. So as theta changes, there is a subtle change of the resonance frequency. The beauty of this changing theta is, without changing the dimension of the SRR, you can shift the resonance frequency. You are not changing the profile, dimension, of the outer ML of SRR. You are just tilting the inner ring of the SRR gradually. As you can see here, there are three pairs: pair 1, pair 2, and pair 3. So they are differently sized and differently tilted also. As you can see here, these are same line. So this is like 0 degree. This is a little bit of offset. So this is like a 60-degree rotation, and this is a 90-degree rotation. Pair 1, pair 2, and pair 3. So these are loaded on the SRRs. On the back side of the substrate, just beneath the CPW feed line, while the CPW feed line basically excites the antenna. So in this particular concept, as you can see from this cross-sectional view and little bit 3D perspective view, now I am introducing two pair of switches. So these two switches, I can actuate them on and off. Probably you are following this particular region, this bit of animation. So these two switches, I can control them on and off. So when they are off, this antenna will behave in one fashion. When they are on, the same antenna will be acting as a different antenna. So sometimes it is acting as a frequency notch UWB, sometimes it is acting as a narrowband antenna, depending on whether those two switches are on or off. So I can have some pin diodes there, and I can actuate, or MEMS also, RF MEMS also, I can actuate them. That means I can configure them on and off by putting a periodic pulse to control the status of the signal. Now you imagine that pair of switches are loaded on the second pair of SRR also. Now the same antenna will behave as a narrowband antenna at a different frequency. Similarly, when the switches are placed in the third place, these will actuate another pair of narrowband configuration. So this was the idea. These are the static shot, and then as I said earlier, so this is one configuration, this is another configuration. You have to see the movement of the switches, and this is the third configuration. I probably start a little bit again. Please follow this particular region in the feed region. So you see here the switches are loaded on the top SRR, which are the largest SRR, then into the intermediate region, and then into the lowermost region where is the smallest SRR. So these 6 switches, actuated 2 at a time, either the top 2 or middle 2 or bottom 2, will actually give rise to multiple narrowband functionality. So actually all 6 switches will be there. By proper feeding nut, you have to control their function. This is the IIST in-house fabrication prototype, which was done by my PhD student. I mentioned his name earlier, Latif, who is at SAC now. So these see with very tiny resonators over here. These are just few millimeters, even smaller than your Tylenol type of tablet, very small tablet. And then you have, this is part of the magnified view. As you can see, this is 0 degree, this is 60 degree, and this is 90 degree. These are the fabricated prototypes. And then on the back side, we have the switches. But the first experiment we couldn't do with the switches because we are not having this kind of facility to embed the switches. So initially, what we did was we placed some static switch in the form of some copper switches. So the copper sellotapes are available. So when I don't connect it there, this is automatically off. But I can put some switches there, and I can remove them also because this is just like sellotape. So these are actuating three different combinations. As you can see, the leftmost one, you have the switches at the topmost region, just on the other side of the theta 0 degree SRR. The intermediate one, you have the switches in the middle region where you have the theta 60 degree SRR on the other side, and the last pair is corresponding to the theta 90 degree. So with these switches, with these three configurations, as you can see the position of the copper strip and the width as well. So you can actually actuate those narrowband resonances and thereby the antenna parameters. So this is basically the antenna size. So this is, let me show this table once more. Yeah. So here, as you can see, like we have different parameters. These are the antenna design parameters. You have the SRR design parameters. Because I said there are three different pairs of SRR. So SRR1, SRR2, SRR3, and the switches, of course. So all these dimensions are depending on the theory and depending on the SRR's resonant frequency I talked about, we have calculated. So this is the circuit analysis, because I said that such an antenna can be very nicely interpreted using the equivalent circuit approach. So these are the transmission line section of the CPW, and these are SRRs, SRR1, SRR2, and SRR3. This is the extensive circuit simulation which was carried out for different kind of antennas, because I said this is half of the equivalent circuit. So you have two are not over here, because another half is there in parallel with this, so it will make it unknown. And this is for one configuration. You see the frequency ultra wideband response with this configuration, and then this is a circuit simulation for antenna 2, which is frequency notch thing. And then when I actuate the switches for different combination of the switches, the same antenna will giving me the narrowband responses. So that also you can confirm. So what happens is when you have these switches, this switch will incorporate some additional inductance. So I'll show in this one, follow very carefully. So this is antenna circuit simulation. So this is the standalone notched case, because you have SRR, SRR, SRR for three different cases. And then you have the circuit, I mean the CPW and the SRR coupled by coefficient of coupling, which is calculated theoretically, of course. And then you have actuating the switches. So these two switches, follow it carefully. These switches are indicated by these two inductors, which are 4LP. I mean, some pi conversation is involved over here. So this is for one case, this is for the second case, and this is for the third case. So depending on which pair you are actuating, you are actually having narrowband 1, narrowband 2, and narrowband 3 respectively. So this is what I wanted to convey. And the summary of this particular information, if you grasp this idea, you can come up with your own design. So this configuration where you have SRR loading and of course the CPW for monopole, it is frequency notched ultra wideband response. Now please look into this area. I'm bringing a pair of switches. When I bring this pair of switches, the same antenna now is acting as a narrowband response. So what I'm doing now, because I have two pair of electronic switches which are pin diodes, or which can be MEMS also, or other kind of switches, photo switches or whatever, I have the mechanism to actuate their operation. So you see, now I am changing the switches. The switches are toggled back and forth between off and mode, and then what happens is the same antenna is toggling frequency notched and ultra wideband response. Right? So this is the very basic mechanism for this antenna. So this particular part I can go a little bit fast now because we have another 15 minutes or so now. So this is the configuration, the same antenna for narrowband operation. As I said, I am showing it little bit, you know, magnified view here because I want to convey this message to you here. So this is a Boolean table kind of thing. You see, when I have 000, I have basically the antenna acting as a frequency not short wideband response. 000 means there are no switches over here. And then when I invite a pair of switches, as you see here, the switches are coming here. Switch is 1, 0, 0. The antenna is acting as a narrowband antenna. Second case, I will have the switches in the intermediate pair of SRR. So from 100, I go to 010 case. This is just for easy understanding, nothing more. I mean, the story I have already told, right? So you have the copper switches here, you get a second resonance mode, second narrowband response. Now you have copper switches here, you are getting the third resonance mode. So this is a useful way to understand the mechanism of this antenna. Notched wideband, narrowband 1, narrowband 2, narrowband 3. So that's the beauty of this particular. And as I explained earlier, this concept can be nicely understood by using the concept of pointing vector. So what is that? Like as I said earlier, you can see this from here. Like I'll be showing to the pointing vector plot now. Triple notch configuration, simulated current distribution, and pointing vector. As you see, so first notch, second notch, and third notch. So you see at different frequencies here, these largest one, smallest one, and the smallest one here, and intermediate one are excited. So these are HMSS simulation. So you can see these are the surface current. So depending on which frequency you're observing, the antenna is never excited thanks to this resonance of the SRR because this is not. And this pointing vector indicates that there are three blue lines which are corresponding to three resonances which are governed by SRR pair 1, SRR pair 2, and SRR pair 3. So this smallest one will be corresponding to this one, and the intermediate one corresponds to this, and this corresponds to this. So this is a very beautiful way to understand this. And more importantly, if you follow this plot, when it is made in a way so for easier understanding of the concepts, here we are observing the pointing vector from this point to this point. Okay, so you see wherever you have the SRR, from that point onwards, you are getting a reduced pointing vector, very less blue line it is indicating. Okay, and that part of the power is not reaching to the antenna. So these three blue lines are indicating three notches. Those notches are contributed by SRR of different sizes. The smallest size corresponds to the largest frequency, largest size corresponds to the lowest frequency. So this is the interesting story. And then if you want to really combine these three notches to come up with a wideband creation, that also you can do here. As you can see, these three resonator sizes are very close to each other. Thereby here also you have three resonances, 1, 2, 3, but their combined effect is something like this. So this is giving you the maximum realized gain, the red one, where the gain falls, and the blue one give you the S1 one. So as you can see, 1, 2, 3, there are three resonances who are pretty close to each other, and they combinedly give rise to a strong stop band, meaning the wider stop band. So this is the stop band which we got almost, I guess, around 500 to 600 megahertz. You can see, you can do this kind of studies, those who are trying to do some research in this particular area of multifunctional antenna and cognitive radio antennas. So, so this is the summary at a glance: narrowband configuration for configuration 1, configuration 2, and configuration 3. As you can see, for narrowband configuration, you have a blue line which corresponds to the resonance frequency of the SRR at the largest, intermediate, and the smallest one. So This was a interesting journey. Till now, I am showing the multifunctional responses, but now I show how those switch configuration from one mode to another mode is done electronically, and finally how that narrowband tuning is also done. Before that, this is another interesting piece of work. This is based on a multi-layered structure. What is multi-layered structure? In our previous work, we are loading the splitting resonators along the monopole. As a result, the feed section is getting a little bit longer, even though it's not that much, because these resonators are very tiny, as I said, just few millimeters of diameter. But still, as a as a reviewer, you can tell that you are increasing the feed length. So we got a comment like that, and that comment was we used in a very constructive fashion to come up with another beautiful piece of work. So the comment was basically, when you are putting another pair of resonator, you are increasing the length. Fine. So what we did was we placed another pair of resonator on top of a superstrate. So this is a superstrate. On this superstrate, we place another pair of resonators, whereas the previous pair is already there on the bottom side of the substrate. So this is a little bit multi-layered configuration, because you have a slotted monopole over here and you have a superstrate. On this superstrate, we have these two pair of resonators loaded, and they are differently sized. That's why you can get two notches. At the same time, you have the switches here. So these switches, if you can activate and deactivate, you can get narrowband as well as notch configuration. And this one, as I told earlier, the circuit simulation part you can do. And this circuit simulation, I recommend everyone to follow, those who have not done this type of work. The beauty is here, it is a co-simulation, because you see here, similarly as I mentioned earlier, SRRs are being replaced by its equivalent circuit, that is the SRR capacitance and inductance, which is divided into symmetrical mode, and then you have the coupling between this. So this is bottom SRR and this is top SRR. That's okay. The more interesting part is what you have, and this section is a impedance. At that impedance, you are saying 100 ohm, because you are saying another 100 ohm will come into parallel to make it 50 ohm. But actually, because it is a wideband antenna, so you cannot call it as a 50 ohm termination. It's a termination which is a function of frequency. So that's why you see here, it's not 2 or not, but it is 2 ZAF. And ZAF is the antenna impedance as a function of frequency. So that is fed over here. And that ZAF you can take from measurement, or you can take from the simulation also. That is from the EM simulation, and then you can fit to the circuit simulation. And this is the input side is mass termination, because here you have a 50 ohm current. So this approach is pretty straightforward, and I mean pretty useful and pretty physically significant. And this is what I said. Finally, the copper switches are very good for proof of concept experiment, but to really claim that these antenna can show multifunctional response, and to have a feature which is required for cognitive radio applications, you have to show that tuning by using electronic switches. So whatever copper switches we had earlier, now those switches are replaced by these pin diodes. So you see, these are the pin diodes, RF diodes, which is the same 0402 type of diode over here, and this is loaded, and it is connected to the network analyzer. So this is the coax RF is going, but then to bias these diodes, you need to have that DC bias applied. So that is done by this bias key. So you have a voltage source, DC voltage source, or pulse also. Then you can keep on switching on and off of these two diodes. And this is the experimental setup, where first time using electronic switch and using a printed monopole antenna which is loaded with SRR, we showed the single antenna can work as ultra-wideband band, notched ultra-wideband, as well as narrowband antenna. So this is the response of the antenna. It's a measured response, and this measurement is not straightforward, because you have to have the sources also inside the chamber or some battery to make this the diodes on and off depending on the situation. So as you can see, this diode off condition, you get notched UWB response. With diode on condition, you get a narrowband type of response. So this is the S11 plot, and this is the maximum realized gain plot. Here also you can see with diode off and diode on condition, you get antenna responses like this. So here the gain falls, and here you get a sizable gain only at the notch frequency. And this is the pattern. I want to show this video. If it runs, you see probably it will run. Just follow this one. It's a real-time video we did while gathering the pattern. Here is that screen of the network analyzer. Here you have the antenna, you have the bias T, the coax, and this bias T, and as you can see, this is going to the vector network analyzer. This is the S11 port you're showing. You see the antenna sometimes, I said now it is a notched antenna. See the screen, and when I apply a pulse, to make the diode configured in a different mode, the same antenna from this mode, you see now all of a sudden it will be going to the narrowband. Just a minute, you see now the same antenna is now working as a narrowband antenna. There are some you know, higher harmonics also coming into picture due to the higher resonance of the SRR. So these actually shows that the same antenna in real time can have two different antenna responses, right? So this is the video, and this is the last part of the presentation. This design concept was further improvised by one of my students, and incidentally, he was a BTech student who did this work, Rajesh, during his 8th semester, just in 4 months. So he designed basically intelligent system like this, where there is a superstate, and this superstate is movable, and this movement is actuated with an arrangement like this, which is called the rack and pinion arrangement, the mechanical engineers thing basically. And this teeth, this the rack and pinion, and was designed, fabricated in-house by him. So he did both antenna structural engineering together, and you see the simulated response that the notches are there depending on the position, because as you have seen in the animation, as the position moves, the resonance moves, and same antenna, when there will be a pair of switches, will be acting as a narrowband antenna also, depending on the position of this. So this is the sizes are changing, pair 1, pair 2, and pair 3, and this is the basic experimental setup. And as you can see from this particular diagram, we have to actuate this rotation. How do we actuate this rotation? So for that, we actually loaded these on a superstate. We use some structure so that these can only move along a line like this. I'll show this experimental setup. You see over here, this part is the teeth, and this is the rack and pinion arrangement. You have a small motor, a servo motor, 10 to 12 gram weight, and this motor is actuated by the Arduino microcontroller. So this Arduino microcontroller drives this motor, and this actually causes the movement of this. So if this moves, then what happens is the superstate moves. If the superstate moves at a time, either this pair or this pair or this pair is actuated, and as a result, this antenna will be acting as a multi-notched as well as multi-narrowband response. So this is the overall experimental setup. The antenna, the superstrate loaded over here. This is the servo motor. The connecting cable, of course, it will go into VNA, and this motor is connected through this Arduino microcontroller, and this Arduino is powered by the USB cable of the your laptop, right? And this part is going to vector motor. This motor is controlled by Arduino, and the specific angular rotation, there was a lot of coding involved over here, because at different positions the motor will stop, right? So this is a pre-coded thing. Arduino, you have to burn, or you have to program accordingly, so that you give certain number of cycles, it will stop. So one mode is excited, again it goes and stop, another mode is excited, and so on and so forth. So this is the overall experimental setup. As you can see, these antenna, the VNA, it's going to the VNA. I'll show that. And this is just our in-house experimental setup, I guess. So this is the overall setup, and this is the Arduino. I think, yeah. So this is the motor. I have already mentioned this, and I want to show this video because this is the name of the student is Rajesh. So I told them to capture that video. Hopefully, to run. Let us see. As you can see, probably by now, let me start it from here. You see, the motor actuates the rotation of the superstrate. As a result, you see on the screen, the same antenna, it is giving frequency notches at different frequency. Okay, so this notch 1, notch 2, notch. You can hear some sound also. So that sound is my voice probably. I was instructing the students to capture a proper manner. You see, so depending on the position of the superstate, you are getting multiple responses, right? So this is the summary of the work, and then this is the summary of the entire work. Ultra-wideband antenna, superstate and SRR is loaded. There are switches also, and the switches and the motor combined it together gives us the tunable notched ultra-wideband function, tunable narrowband function. So 6 different antenna features are actuated from a single antenna. This is the last couple of slides where I told that the narrowbands needs to be reconfigured. So these we have done. One of my MTech students who is in RRI in our Raman Research Institute, she was so sharp and this amount of work. So varactor loading was done on the SRR. So these are not now SRRs; these are varactor loaded SRRs. Because of the varactor bias change, these antennas, it is a tapered slot antenna, Vivaldi type of antenna, as you can see, and the varactor loaded SRR placed beneath this section where the this microstrip actually excites the slot, and the slot is tapered to actuate the radiation. As you know, this antenna is a end fire type of radiator and with a maximum radiation in this direction. But typically it is a wideband antenna. But when we have a switch over here and we have a SRR, together it will act as a narrowband antenna. And when that SRR is controlled by a varactor diode, SRR's resonance frequency will change. So now these antenna will be acting as a multiple frequency notch and multiple narrowband antenna with continuous tuning. Continuous tuning because the varactor bias you can control continuously. So this is NB1, NB2, NB3, that is notch band 1, notch band 2 and notch band 3 respectively for different capacitance of the varactor. So these capacitance are actuated by proper bias voltage from 0 volt to 20 volt, and this antenna was measured in RMC Canada as well as SAC Ahmedabad Space Application Center. So this is the notch configuration because there are so many cases, so we are not showing the simulation and measurement together. This is the simulation and this is the measured situation, and this is the narrowband configuration for 3 different varactor loaded SRRs. A very beautiful, almost octave bandwidth is obtained. 1.1 gigahertz, 700 megahertz, and 1 gigahertz. So if you add them up closely, it is 1.1 plus 1, 2, and almost 3 gigahertz or 2.9 gigahertz kind of narrowband tuning is achieved in our antenna. So this is quite unique, and you won't see any such structures reported to you. So because I talked about pin diodes and varactor diodes embedded in our work, and then another option is RF MEMS. So if you really want to have this type of antennas integrated and make it operational and commercial, you have to know the features of different kind of switches and different kind of tuning mechanism. So this is a screenshot from one of the pages of my book, and there you can actually compare the pin diodes with RF MEMS and the varactor diodes. And then we had done some work and we were using pipeline further at using mechanical actuation using the MEMS, cantilever with MEMS switches also. such an antenna can be actuated. So this is a glimpse of that particular work. So with this I come to the conclusion and some kind of information sharing that we have certain kind of facilities like almost all CAD tools. We have major equipments like signal generator, spectrum analyzer, VNAs, the PCB prototyping machine with 100 micron capacity, and then last one, the far field anechoic chamber up to 40 gigahertz is in the process. So with this, I acknowledge my collaborators, the different government bodies, ISRO centers, and some of the foreign labs. And also some part of the work has happened, and also IEEE funds because it helps us in presenting the paper in different forums, and sometimes travel supports and other kind of thing. Some other work which I did not show here is happening with semiconductor lab, and on some of the other things we have worked with Isaac Trivandrum. So whatever I presented was a long journey, and as you understand, during this long journey, many students, many people have worked with me. So the topmost left one is IIST PhD student who did very extensively, has done very good work, and because of his vision and dream, he immediately joined to ISRO Space Application Center, Ahmedabad. And then we have NRSC Hyderabad, and there are other students. It will take time if I describe them all of them. But all of them are assets, and because of their work, this work has flourished, and also to our collaborators like Professor Siddiqui and Professor Yahya Antar. So the most part of the talk is based on the published article. The 5G part of the talk is based on our recent work, which as I said, that they are in a 5G forum conference. The paper will be in Explore soon. And other part of the work is based on our journal articles, all are in IEEE here, and the book which is published last year with Taylor and Francis. So with this, I conclude. I thank the organizers once more, and these are the two books organizers talked about when they introduced me. The left book is the book which is connected with the talk, but the other book is a Cambridge University Press. I started writing this book long back when I was very young. I got an offer, and then Cambridge was very interesting and very lucrative at that time. But then in between, I thought I won't be able to complete, and I, requested some co-authors. They also helped little bit, and finally we came up with this one. So with this, I conclude my talk with a small announcement that there are some positions available in my group for PhD positions, as well as with respect to some positions in BST ACRB project. With this, I conclude my talk. Thank you very much for inviting me in this prestigious workshop. Right. So, yeah, over to you, to the organizers. Now we can definitely interact. And thank you very much again.
Thank you, sir. Now the session is open for discussion. Participants can clarify the queries with resource person.
Sir, we have posted your book link in the chat box. Since participants requested, we have posted in the chat box.
Thank you.
And queries raised by the participants I have given in the chat box itself, sir.
Okay, so you want me to see the chat box? Okay.
Yes, sir.
Okay. So I'll go from the top side, right?
There were 9 queries, sir, listed.
Only 9. I thought I'll get more. Okay, so I stopped sharing so that I can read it effectively. Yes, sir, you are audible. So these are not queries. Okay, maybe I'll start from the bottom side. Feedback link. Okay.
Sir, just last, sir.
Okay, 9. Okay. Where the excitation points are getting changed in the setup set. Is it like which? The 9th question.
Sir, I will post it again, sir.
Yeah.
So I have posted the 6 questions, sir. The first question is how do we categorize
Okay, how do we categorize primary and secondary users during transmissions? Okay, it's a good one. Primary users are the perpetual users. Like you are the owner of your house, right? So you are the primary user. But if you know the Airbnb model, if you want to allow other users to use your house when you are a little bit idle, they are the secondary users. So secondary users are users with less priority, and they will be given the opportunity all the time, but their spectrum will not be fixed. They will be getting the spectrum depending on the available white space. So they will be moving from one place to another place. So like when you go for a train journey, you have a confirmed booking, you are the primary user. If you don't have a confirmed booking, it can assign you in different positions in different time. So that is the idea of secondary user. Just an analogy. But here the secondary users are the users who will have priority depending on the available white space. And for that secondary user, the reconfigurable communicating antenna is needed. Okay. Sir, please explain how to make biasing for pin diodes after fabrication. This is a very good question. In fact, this requires a lot of thinking and a lot of expertise. In the sense, you have to have the bias pad for the pin diode, and depending on the type of diodes you will be using, biasing means what? Here it's a digital, so you have to have like typically 3-volt kind of bias you will require. Depends, maybe 5-volt also. So those signal lines and ground lines, you are having the diode there, but then you have to temper or you have to have a bias pad where you will be applying these signals. So that part, when you do, you are applying the DC, but you really don't want the DC to interfere with RF. So some chokes and some filtering mechanism would be needed also. So bias pad is a professional arrangement. But in real time, as the last part of the work I was showing, where Utw has done that, the last part, like with the Vivaldi antenna. So there, the bias part is integrated and the diodes are loaded accordingly, and then we have applied this particular kind of voltage. Okay. These radiation patterns are from HFSS or CST. So the simulated pattern that I have shown for most of the antennas are from HFSS. But most of the pattern that I was showing, especially for cognitive radio antennas, are from measured. So neither HFSS nor CST, because we believe on the measured pattern. Of course, simulation will give you ideal pattern, but our results was based on HFSS when I have shown the simulation results. But when we have shown measured results, it is from the anechoic chamber at different places. I hope it clears your doubt. Question number 4, sir, how fidelity factor of ultra-wideband antennas be calculated? It's a good question, but it's a basic question. So please go to the fidelity calculation, so which will be based on the parameters of the antennas. You can get it, and it is not only the fidelity. You have to see the ringing, you have to see the group delay. So all together, you have to see. Question number 5 is how metamaterial is different from frequency selective surfaces. This is yeah, it's a good question. I would say they're related in the sense, but in FSS, not always we are talking about this. The extraction or the other kind of applications. But of course, they are strong correlation with each of them, and there is different ways of defining and creating the simulation environment depending on the surfaces. So from that aspect, I can say it is related. You can go into the details of the work. Like in FSS in India, there are some people of work who have done good amount of work. Like in ITT, Professor Raghavan's student, he has also done good work. And then there are other people in IITs like Dr. Ghosh and then Dr. Shomov. They have done good work on the FSS kind of applications. But as far as our work was concerned, we have used the metamaterial ideas to apply on antenna fronts. That's why I was naming them as metamaterial inspired antenna. Right? So question number 6 is what I exactly said now. How the metamaterial inspired antenna achieve both negative permittivity and permeability, whether both be negative simultaneously. Actually, there is nothing that metamaterial antenna. You use some kind of metamaterial structures to actuate some phenomenon, as I was showing here, or some people are using metamaterial structures to enhance the antenna performance, maybe antenna gain or meta surface for changing the polarization or changing sometimes enhancing the gain. So it is, the material concept. This is a very, wrong idea to use some kind of resonators and call it a metamaterial. So for a material, as you understand, material is all about a homogeneity, all about a isotropicity, all about having a 3D periodicity, which cannot be obtained by just using few resonators. That's why I refrain in saying that these are metamaterial antennas. These are metamaterial inspired antennas, some of the structures I was showing. Okay, so this is a good question. I also always encourage, but be very careful. Don't call them metamaterial antenna if you are working in this area. This is a very wrong idea. Question number, I think question number 6 I covered. 7. Is it possible to use the metamaterial unit cell for the radome applications? Yeah, it's very, very useful. Like a metamaterial unit cell, you can do frequency selective applications, or you can go for gain enhancement. I was showing some horn antenna there, right, for frequency notching for NRSC applications. But same SRR kind of structure can be used for radome, and also sometimes it can be used for the gain enhancement and the aperture of the antenna. If you see the different FSS structures have been applied on the horn aperture, the idea is, without going for a long aperture, which will increase the size and increase the weight and other complexity, just putting a surface, which a FSS kind of surface, you can enhance the gain, you can do kind of filtering, you can ensure without even a filter section at the receiving end, after the low noise amplifier, you can have an embedded systems with inherent frequency notching application. So these are the extension of it. Okay. the okay, so the question number 8, whether these are used for space applications. Yes, definitely. Space application, when you say antenna, is for space applications only, but typical space application means what people means is, it is probably the ground station applications or antennas for nanosatellite applications or the transponder applications. So people are trying to see different kind of applications. So yesterday, probably, I don't know any one of you are there or not, one of my PhD student who is a scientist at NRSC Hyderabad, he was talking about on a lot of antennas, but it involves big work, a different skill set and a different ball game. But on some of the antennas, some metamaterial structures are being conceived. For example, I was talking about the horn antenna. NASA is using the ideas of metasurfaces for different kind of applications. Okay, so it has applications in space as well. But in general, when you talk about the space antennas, the other complexities are more important. Other complexities means if it is a unfurlability, or it is some kind of very high gain requirement, if you think of the satellite transponder and downlink kind of application. And that station also, you need a very, very high gain antenna, because your beam is just a fraction of a degree kind of beam, the HPBW, if you see. So this is very crucial to understand that different applications requires different set of applications, because different set of skill set. These antennas are good for electrically small antennas. Like Professor Zilkowski was one of the pioneers on metamaterial antennas. So he has shown basically that some 0th order resonance and some wavelength resonance and sub-wavelength structures to come up with a different kind of electrically small antennas. In my NIT Trichy's physical workshop, which happened in February, the DST Spark workshop probably. So there I spent a lot of time on the electrically small antenna, but today, because the talk was mainly focused towards 5G and cognitive radio, I didn't talk about that. But I could have extended in that side as well. But you see, They are quite applications of metamaterial antennas, but not exactly for space. But metasurface might have some component. And then, as I said, for ground station applications, for especially for spatial filtering or some frequency rejection, etc., these antennas will have some applications. Okay, so I think the ninth question, whether the excitation points are getting changed in the setup. I'm not getting this question. Can you unmute whoever has asked this?
Sir, you have shown one experimental setup at the end after this multifunction antenna. In that, you have moved the antenna side by using a actuator on left hand side. So at that time, the cable was connected with your CRO measurement equipment. So at that moment time, whether the excitation point also getting into change because you get a different notch at the different places at that time. So you get the different notch at the different places when the antenna structure is moving on the left and right. That is the only expectation of myself.
Oh, I got your question now. No, actually, antenna is not moving. The part which is sitting on the antenna, that is moving. Suppose I don't have anything here. Suppose this is the antenna, and this is the superstrate. Okay, I hope you can see this now. So this part is actually moving like this. This is the superstrate. The superstrate is moving. So antenna is not actually moving. Here you have the cable, and that goes to the vector network converter.
Fine, sir. Understood. Thank you, sir.
Yeah. Thank you. So, thank you to the organizers once more.
Thank you, sir. It was excellent lecture. Let us please conclude, sir. We will conclude it, sir.
Yes, please.
Before winding up the session, hereby I want to convey this to you, sir. It was a wonderful session. All the information was very useful, sir. Especially introduction to the metamaterial with animated simulation results makes the participants more clear. And fabricated antennas for ultra-wideband, metamaterial inspired and cognitive radio applications which you have shown with measurement setup is more informative, sir. And also you have given a clear idea about how it actually arriving from 4G to 5G till 2025. And recent antenna for the 5G application was very useful, sir. And also you have mentioned your students on all your presentation. That is very impressive, sir. Thank you, sir, for enlightening us with your informative presentation. I hope that the participants gained more knowledge on antennas for cognitive radio and 5G applications. I extend my sincere thanks to Dr. Chinmay Saha, sir, for spending his valuable time for us. Thank you, sir.
Thank you very much. Stay safe and stay well for all of you. Thank you. Bye.
Thanks a lot, sir. Take care, sir.
Thank you, sir. Thank you all the participants. There is an announcement. Now the session is winded up. The next session will start at tomorrow morning by 10 a.m. All the participants are requested to join at 9:50 a.m. via the Google link which we sent. Thank you one and all.